right? So so let me begin with the definition. So, of course, throughout M will be a smooth manifold, which is dimensions. So it's an n manifold. And for the definition of a vector field, I also would need the tangent bundle. So remember that the tangent bundle is a 2n dimensional manifold. It's a 2n manifold where at each point of M you kind of look at the tangent space as well. All right, so what's a vector field? So the definition, so this is of course a smooth vector field. That is what we are after. On M is a smooth map. I mean, yeah. So I mean, all maps for us are smooth anyway. But it's a smooth map from M to the tangent bundle, such that the projection back to M gives you the identity map. Let me call it the identity map on M. Okay, so remember there's a projection, that's what I was calling pi, from the tangent bundle to the underlying manifold, where the point P comma vector goes to the point P. Okay, so that's this pi over here. So this kind of map is also called a section. It's a section of the tangent bundle. Okay, so sections of the tangent bundle give you vector fields. All right, and so what does it really mean? What does it give you? Well, it gives you, for each point P and M, what is S of P? Well, it's a tangent vector. So this defines a tangent vector in the tangent space at P. Okay, so it has to be a tangent vector at the point P, because you know that pi composed with S followed with pi is the identity map over here. Okay, so this guarantees that, ensures that this is some tangent vector in this particular tangent space. Okay, right, so in other words, so if you, here's your manifold. Let me just now sort of maybe draw a picture. Sort of this blob is your manifold. At every point P, you have a tangent. Tangent. This is one tangent vector nearby, another tangent vector, and so on. So this is what a vector field looks like. And then you've encountered vector fields in R3, I'm sure, and R2, and you've done calculus. So this is the definition on a manifold, right? And not only a tangent vector, I should also say that, and since the smoothness, so maybe defines it that varies smoothly. So the smoothness of the map S ensures that this tangent vectors, they vary smoothly as you move around in the manifold, right? So that defines the tangent vector that varies smoothly as you vary the point P in M smoothly. Okay, so it's so that's what a vector field is. All right, and so so this is somehow some kind of a global definition, but locally you can use charts to sort of describe vector fields. So locally, so suppose you look at a coordinate chart U. Let me give, instead of talking about the map phi, let me just give coordinates. So these are the coordinates x1 to xn are the coordinates on this local piece. Okay, that's you can think of U as an open set that's parametrized by some open set in Rn, and the coordinates that you obtain on that open set U is given by x1 to xn. So this So if this is a coordinate chart on M, then what does this section, what would it look like? Well, this section just defines this vector field would, so at every point it's a combination, it's a linear combination of some of these coordinate vectors. Okay, so remember that's what we saw earlier. So if you have a coordinate chart, then so the coordinate vectors, let's say this is some piece in R2, then you have these coordinate vectors del del x1, del del x2, and this you view it at any point. Okay, so sort of any point x, maybe I'll call it P. Okay, so because I'm already using, let me call it P. So at any point P, you can talk of these two coordinate vectors in R2 and Rn. You have n of them. So, and every point P, you can talk of a linear combination where you have these coefficients AI, and these AIs are also functions of P. Okay, so these are AI of P, and so for any P in U, you can describe your vector field as this kind of sum where these coefficient functions AIs are smooth functions. So these guys are smooth functions, and these are all sort of telling you, specifying the tangent vectors at every point. Okay, so where, let me just write that down. So where each of these A1, A2 to AN are smooth functions defined on U. Yeah, anyone has a question? Okay. All right. So this is what sort of locally your vector field would look like in a coordinate chart. So the first remark. So let me give you a few remarks to all this. So the first remark is that there are lots of vector fields on a smooth manifold. Okay. So in fact, one useful thing to remember is that if you are given a point P in M and some tangent vector in, yes?
Sir, S is a map into TM, right?
Yeah, that's right.
Yeah, then the coordinates should be like P comma something, P comma vector V, isn't it?
No, yeah, that's right. Yeah, so that P is, yeah, I'm not writing it here. That's just, yeah, right. You're absolutely right. So, but what matters is this, the vector field is given by these guys. Okay, so this is what is important. Okay, so yeah, you're right. I mean, maybe I should have written sort of P comma something, but that's sort of a redundant kind of thing, right? So this thing is kind of redundant. It's just the identity map on that factor. Okay, so what is more important is on the, so how the vectors vary, right? So we already know from this property that the vectors will belong to the tangent space at that point P. So that's why I'm sort of restricting all of these to P. Okay, so this we already know. So what's more important is, yeah, so these coefficient functions. So the point is that these coefficient functions are what to determine the vector field. Okay, all right. Okay, right. So so now let's let's come back to this remark. So given a point P in M and X in TP of M, there exists a a smooth vector field x tilde on M such that at the point P, the vector is x. Okay, maybe I should write P comma x if you want to think of a section as you were mentioning, but usually I'll just sort of forget about, what it really means is that every point and you want a vector. Okay, so I want the vector. So here I've been given a vector at the point P. Okay, and I want a vector field, a smooth vector field on the whole manifold, so that at that point P, it is that vector. Okay, so this you can do. So this immediately ensures there are lots of vector fields on any smooth manifold. You can have a vector field with a prescribed vector at a particular point. And how can you do this? Well, you use a bump function. Okay, so let u comma phi be a chart around P. Maybe I should have written x1 to xn here. But anyway, so such that this vector x is a combination of these xi's at P, okay, in these coordinates, where these ai's are now real numbers, right? And then you choose a bump function rho from u to r. This is going to be defined on that chart so that this rho at the point P is 1. Maybe you can make P to be the origin in these coordinates if you want, but right now let me just call it P. Okay, and suppose, and you also want, so here's the picture. So this is a U, the point P, and I want this rho to vanish in a neighborhood of the complement of U. So in other words, I want the support of rho be contained in V such that V closure is contained in U. So, okay, so this is something like this picture. So this is, you can always guarantee. Okay, and then, so once you have this bump function, you can define the vector field on the whole manifold as saying that, well, it's just rho times, so let me write rho of P times that vector that we started off with, del xi P. Well, that's on, so if P belongs to U and it's 0 otherwise. All right, and so this is going to be a smooth vector field. The only non-zero vectors are inside this coordinate chart. In fact, inside this smaller set V sitting inside U, and it's certainly smooth there because if you restrict yourself to V to U, it's this guy, which is it's a smooth vector field. So these coefficient functions are just a constant times rho of P. These are smooth functions. So that's a smooth vector field, but it kind of smoothly extends, away as well because, well, I mean, it's already 0 by the time you've reached the boundary of U. Sort of you're already 0. And it's sort of, so this guy you can easily check is smooth everywhere. All right, so this is how you can extend a given vector to a vector field on the whole manifold. And a similar argument, so let me just mention that a similar argument will actually tell you that if you have n sitting inside M as an embedded submanifold, right? So if this is a submanifold, then a vector field a vector field on N can be extended to the vector field in a neighborhood of N, and in fact, if you're also a closed submanifold, can be extended to a vector field on M. Okay, so if you're an open submanifold, you might run into trouble, I suppose. I mean, for example, if you look at R2 and you look at, you throw out a single point, right? So then, you might have trouble. Suppose you have a manifold on R2 minus a single, so you have a vector field on R2 minus a single point. That's an open submanifold of R2. Then you might not be able to always extend it to that missing point, so you might run into trouble. But if it's a closed submanifold, you can always extend it to something, so smooth manifold on M, and sort of the argument would be something similar to what we just did. You kind of you cover it with suitable sort of open charts, in which this manifold looks nice. Submanifold always looks like a slice, right? And then you kind of use a bump function to extend it, sort of everywhere. All right. So this is a useful fact that we'll use quite often. Maybe I'll consider putting it as an exercise in the next homework. All right. So anyway, so this ensures, the first remark ensures there are lots of vector fields, and you can extend things from nice enough subsets like a point or closed submanifolds to sort of the whole manifold. The second remark, well, this is a sort of easy but important fact. Vector fields can be added. Okay, so you have an additive structure on the set of vector fields. Okay, so if you have, let's say, two vector fields y and z, you can talk of the vector field that you get by adding y and z. Well, what's that? Well, at the point P, it's going to be the vector that on the tangent space where you add the vectors assigned by y and assigned by z. Okay, so just because each tangent space is a vector space, you can do this addition of vectors there. So now if you have two vector fields, at every point you can do this addition, and you can get a new vector field. All right, so you have this kind of, so it's a set of vector fields itself forms a vector space. Okay, and it's a huge infinite dimensional vector space typically, right? Because you have, the first remark tells you there are lots of vector fields. Just like you have lots of smooth functions, you have many vector fields. All right, so this is one, and the other related thing is that vector fields, not only is there addition, there's multiplication. You can multiply a vector field by a smooth function. So vector fields can be multiplied by smooth functions. What does that mean? Well, if you have a vector field, y is a vector field, and f is a smooth function. So I'm going to write f as something in C infinity of m. So that's a smooth function. Then you can think of f times y. Okay, and what is it? Well, it's some vector field where at the point P, the vector is f of p times yp. Okay, so yp is a vector, and you can multiply with a real number, it's a scalar, and that gives you a new vector. So this is a new vector in the tangent space. So if you define it like this, then it's going to be a new vector field, and it's also going to be a smooth vector field, right? Because f was a smooth function. Locally, in local coordinates, these a1 to an that we saw before, they just get multiplied by f. All right, so that's still a smooth vector field. So these two, so 2 and 3, So let me just say that these 2 and 3's tell you, so in algebraic terms, you can say that the set of all vector fields, or smooth vector fields, on M, and this is, let me call this set tau of M, is a module over C infinity of M. So the functions, all these functions. So this is just some terminology. It doesn't really, it just sort of tells you that these two things happen. Okay, so you can add vector fields and then you multiply by functions. All right, so any case, so these are some basic sort of remarks about vector fields. But there's another way of thinking about vector fields. Just like we saw, tangent vectors can be described as operators acting on functions on the manifold. So here a vector field is actually going to be an operator. So it defines a linear map y from smooth functions on the manifold to smooth functions on the manifold. And what is this map? Well, it takes a smooth function to what we'll denote as yf. Okay, so where yf is going to be a new function. So at a point P, it has to take some real value, right? And so what is yf at P? Well, it's defined to be yp. That's the vector assigned to the point P by the vector field y applied to F. Remember that a vector is a derivation, right? So derivation acts, so this guy, so let me just say that, so this guy, so yp belonging to the tangent space M is a derivation at P. Okay, so the derivation at P acts on the smooth function F and gives you a number. And that's the number which is yf of P. And this guy is going to be a smooth function because you can check this in charts. So locally, if you write your vector field as we were doing, just keeping track of the vectors, you can write your vector field like this. So then if you apply it to a function, then what does this operator look like? The operator would just look like taking applying these partial derivative operators on f. Okay, that's what a derivation was at every point. So it would look like something like this. Okay, and this is a smooth function, right? So I mean, so to check smoothness, you need to check locally what happens locally. So locally in a coordinate chart, this guy is definitely smooth. Okay, so since f is C infinity, all these guys are smooth functions, and these were smooth functions because your vector field was smooth. All right, so and in fact, it can be also this can be considered a definition of a vector field also. And so let me just note that at least the smoothness part kind of is a consequence of so yf is smooth if and only if the vector field y is smooth. Okay, so in other words, these A1 to A2 to AP are smooth. Okay, so in any case, so you can actually sort of also derivations are linear operators, and so everything sort of splits as a sum. Okay, so so this is a linear map, but it has one more property. Just like we saw the derivations, satisfy the Leibniz rule. Here, this key property is the following. So if you take y, maybe let me switch back to black. So property that we'll care about is if y of product of two functions, if you take, then it's going to be f times yg plus g times yf. It's a product rule. This is for all fg in C infinity of m. So you can call this the product rule. So the product is some property of this linear operator that we define. Okay, and sort of the definition extending the things that we discussed at the level of tangent spaces and points earlier, you can now define a linear operator, linear map, y from C infinity m to C infinity m is a derivation if it satisfies the product rule. Okay, and the fact that I leave to you to kind of check, it's very similar to how we did things at the level for derivations at points. We saw earlier that if you have derivations at points, then they correspond to vectors, right? Tangent vectors. So they correspond to directional derivatives along some tangent vector. And so if you have a linear map like this, satisfying the product rule, so it's a derivation like this, it actually always arises from some vector field. So the fact that is that any derivation arises from some vector field, smooth vector field. Okay. Anyway, this is maybe I'll treat it. You can treat it as an exercise, right? So anyway, so there's this other point of view. So very often we'll be thinking of vector fields as something that can act on a function and give out another function. Okay, this is going to be a point of view that we'll very often use. Okay, so this is sort of so some discussion, right? Now the other thing that you can do with vector fields, like we did for tangent vectors, is push forwards. So let me now sort of come to that. So push forwards of vector fields. So
could you update the lecture notes?
Yeah, sure. Who was that, by the way?
Yeah, Preetham.
Okay, Preetham. Okay, right. So I've updated it. You have any questions about any of the definitions?
No.
Okay. All right. Yeah, thanks. Let me know whenever you want to update. All right. So push forwards of vector fields. So how does this go? Well, so what do you want to do, really? I mean, so you want to say that suppose you have a map between two smooth manifolds, F, right? And suppose I have a vector field here, right? So I want to sort of define a vector field on N, right? And so one way to do it is, you have this map. So suppose I look at a point P in the manifold. So at the point P in a manifold, you have a tangent space and your vector field, let's call that vector field, I don't know, y. Okay, so this vector field is y, all right? This is a vector field on M. And so you have a vector yp in the tangent space at that point. So what can you do? So you can maybe define, so you know that the derivative of f, so df at the point P is going to be a map from this tangent space to the tangent space f of P of n, right? And so you can look at the image of that map, right? So image of that vector under this map, right? So as you're looking, so yp goes to something, and we'll call that z of fp, right? So this defines a vector here, and so this is a sort of a kind of the first attempt at what you would, want to do, right? So you would want to sort of push forward via a smooth map, and so when you look at the derivative and sort of look at where the vectors go. Except that you run into trouble if your map f is sort of f is not injective or something like that, right? Or if yeah, so maybe I'll stick to, I mean, so suppose you have another point Q here, which also maps to the point f of p. This was our, I should have called it f of p here. So it also maps there, but there the derivative, sends the vectors somewhere else, right? And so then you would run into trouble in defining things, right? So you can't quite define it for all smooth maps, but as so you can do it for diffeomorphisms at least. So sort of this is something where you don't have any trouble. So if fm to n is a diffeomorphism, and y is something in the vector field in M. I already introduced the notation tau of M. That's the set of all smooth vector fields. So so if you have some vector field on M, then the property of that push forward that I just defined, there exists this unique vector field on N, such that, so this, what it does is it, as an operator, so this equality holds, this identity holds. So if you think about the vector field Z, it's going to be an operator on functions, smooth functions on N. So here in this picture, there will be some smooth function, real valued thing defined on N. So it will operate and give you some smooth functions. So whatever smooth function you get here, and you also get a smooth function when you look at this composition. This is a smooth function on M, and you apply it to Y. Okay, and so Y operating on this smooth function gives you this smooth function. That's just going to be a composition of this guy with that. So there's some kind of nice composition rules, satisfied by this. And if you think about it, this only happens if what I just said takes place. So if the f star of, or df, I mean, I sometimes call the derivative f star of yp, the vector yp is z of fp. Okay, so if you have a diffeomorphism, you can always define your vector field just by pushing forward at every tangent space, and this push forward vector field satisfies this kind of property that I just mentioned. Okay, so it's going to be yes.
So basically, here we encountered a problem while defining the push forward. So we are saying that f must be a diffeomorphism. Essentially, Is
Right.
this because we will not encounter the same problem when we define a pullback? And in diffeomorphism, what we are doing is we are defining the push forward of f as the pullback of f inverse.
Yeah, you can think about it that way. That's right. Well, I mean, even for a pull back, how do you pull back, right? I mean, how do you do that?
We will not have. I mean, if it's invertible, it has to be bijective. So we will not encounter the situation which you just pointed out for a push forward in the previous case, where P and Q map to the same point. Then it won't be invertible. So um,
Yeah, but a pullback, you run into the same kind of issues, right? I mean, you can't always define a pullback of a vector field, right? Where do you pull back to, right? So suppose you have a map f from m to n, right? Oops, I wanted to call this m. This is f n, right? You have a vector here. Let's say a point p here and a vector here, right? So yeah, you don't quite know. I mean, first of all, P might not be in the image of F. Then what do you do? But even if it is in the image of F, there could be several points that are in the image of F.
so is it not possible
Pre-image.
to pull back to all of them?
But what do you define it as? I mean, how do you, what vector should, so suppose there's only one pre-image. Let's say it's just one pre-image. So what vector do you put there?
There would be
Right?
some charts, right? So we can map according to those.
No, what does that mean? So, I mean, suppose you have a vector x in the target, right? And so suppose there's a point, let me call it, since we are looking at the target, let's call this q and this vector y. And suppose p maps to q, right? F of p is equal to q, right? So what vector do you want to assign at p? Right? There's no natural choice, right? I mean, yeah, what do you put there? It's not clear, right? I mean, if you just assume f is a smooth
I mean,
map,
it should be like at least the guess should be like dfp inverse of y, right?
yeah,
I
but
mean,
then it should be, they're already assuming it's invertible.
yeah,
Right?
yeah, but I mean that's the
Derivative
choice,
is
exactly.
right? So you're already assuming certain things about f, which so it can't be, you can't do it for an arbitrary smooth map. That's the point, right? You can certainly do it for a diffeomorphism. That's sort of the point here. You can push forward, pull back, whatever you want. For the diffeomorphism. Diffeomorphisms, you can just, sort of move vectors around. Diffeomorphism is essentially a kind of a relabeling of points, right, on a manifold. Anyway, so, right. So, but sometimes you can, sort of can define it for other maps. I mean, you could be in a position where, P and Q both map to f of p, but the derivatives map, the vector field vectors to the same vector. Then you have no problem. Then there is no ambiguity, and you can actually define it. So let me just say that. So you can define it. So sometimes, and let me just say that sometimes there exist vector fields. So let me just say first that sometimes if f is some smooth map, so is a smooth map, not necessarily a vector field, sorry, a smooth, a diffeomorphism. I'm getting ahead of myself here. Not necessarily a diffeomorphism. Then there's this vector field. So there could be a vector field Z on this target manifold that is a push forward. So such that this boxed relation, let me call it something. Let me call that star or something. Sort of this relation sort of star holes. Okay. Okay, and so you know when that happens, right? And so when basically, you know, whenever there is this ambiguity, you know, sort of somehow your map F is such that, you know, so this, the derivative maps the vectors at these 2 points P and Q to that same vector, and so you're kind of you don't have trouble defining this as a push forward. All right, so and this is and let me actually, so we'll run into this a few times. This is when this happens, we'll say when the star holds, we say that either we say that Z is a push forward of Y, or under F, or another notation is in Y and Z are F related. Okay, this is something that I think Lee's book uses, and it's sort of convenient sometimes. So these two vector fields are related by that smooth map. Okay, if this kind of composition, if you think of them as operators, this composition works out. Right? All right. So let's see. So maybe I should do some examples. Let's see. So
Sir, you said vector fields form a module over C infinity M. I mean,
yeah.
I mean, do you have something nice there? I mean, if M is compact, then it is some nice module or nothing.
What do you mean by a nice module?
I guess I forgot the exact definition, but I mean, Noetherian and.
No, these are, I mean, you can think of these, I mean, essentially these are, it's a huge, infinite dimensional, right? And you have lots of smooth functions, right? So it's, I don't think it's nice in any such way. It's just a compact, convenient notation for you know, sort of talking of these two things, right? So yeah, I you know, sort of nothing occurs to me offhand that it leaves me sort of nice in any particular way. One can ask lots of things. I mean, so once it's a module, you can sort of talk of, you know, think of all this algebraically. I mean, it's already, one is thinking of it as algebraically as these linear operators and so on. But, you know, typically these will be sort of between infinite dimensional spaces. These are operators from C infinity M to C infinity M after all. So unless you impose some other conditions, yeah, so of course, if M is compact, that's one sort of condition, but I mean, yeah, so for example, a C infinity M, you can ask, you know, questions about that, algebraic questions. That's also some kind of ring, right? So it's, so you can ask whether that's a Noetherian ring and so on and so forth, right? So anyway, so yeah, so whatever is true for C infinity of M is probably, you know, you can sort of gets inherited by these are essentially locally, these are a collection of smooth functions. These are given by A1, A2 to AN. All right, so yeah, I won't be, you know, sort of bothered about the algebra part of things so much right now. Maybe sort of later when we connected with Lie algebras. Okay, so yeah, so maybe I'll skip, you know, sort of some, you can sort of try to work out some examples of things which are F related and not. Let me just sort of, maybe I'll just mention something very briefly. So for example, if you look at the vector field, so this is something you must have come across in multivariable calculus. So your vector field, let's call it Y, is X del y minus y del x, right? So this is on R2. right? And you can try to right. So you can try to see. Maybe I can think of it as R2 minus the origin, and then maybe I can think of a diffeomorphism from F from R2 minus origin to R2 minus the origin that takes, let's say, xy to what's going to be a diffeomorphism. Maybe let me change coordinates. So maybe I'll let's say I have diffeomorphism from R plus cross R that goes to basically polar coordinates, x squared plus y squared, tan inverse y by x, something like that, right? And you can call the coordinates here r and theta, right? And one can try to see where this vector field y gets pushed forward to, right? So you can write down the vector field, the push forward vector field in terms of r and dr and d theta, right? And the coefficients and functions of theta. Anyway, so this is something you can work out. Let me not try to do this here. But whenever you have a smooth map and you have some vector field, you can try to sort of write down what happens to the push forward, and the way you do that, you sort of understand what happens to the derivatives, right? And so anyway, we'll do more examples in a bit. Maybe next time I'll try to do some more examples. But the key thing that I want to get to is what happens in a Lie group, and so this is what I wanted to get to today. So you have what I call left invariant vector fields on a Lie group. So a Lie group is a manifold, and you can talk of vector fields on a Lie group, but you can also have some special vector fields which are left invariant. So what is that? So if G is a Lie group, then you can talk of left translations. Okay, so what is a left translation by some group element? Let's call it A. It's a diffeomorphism of G to G that you get by multiplying on the left by A. So remember that a Lie group has a multiplication, and so you can multiply an element G on the left by A, and this defines a map. Of course, it's going to be a diffeomorphism because there's an inverse, because if you multiply by A inverse, then you go back right to the where you were. So you'll get the identity map as a composition, right? So these are special maps. These are smooth maps because on a Lie group the group multiplication is smooth. So okay, maybe I should just say smooth map, so you also similarly have right multiplications. Okay, so similarly a right multiplication, a right translation. Maybe I should call it a multiplication. Anyway, it doesn't matter. One often calls the multiplication a translation in a Lie group because, for the simplest Lie group, which is the real numbers, addition is like translation, right? So you're kind of your addition of points in Rn are like adding vectors. And so over here, if you think of Rn, if you do a left multiplication on the left by this fixed element A, which is a fixed vector in Rn, it's like, translating by that fixed vector. Okay, so every point shifts by some constant amount. So in general, of course, for Rn, it's an abelian group, so left and right translations are basically the same. But in general, right translation is when you multiply on the right by that fixed element A. Okay. So maybe I should do that in green. Sorry. Right translation is some map which is called R subscript A. A is going to be fixed, and you multiply on the right. Okay, and this is a smooth map, and not just a smooth map. I forgot to say it's actually a diffeomorphism, right? So actually a diffeo, because as I said, multiplication by A inverse would be the inverse map. Anyway, so a definition of a left invariant vector field is as follows. So vector field, this is going to be a vector field, let's call it Y it's a smooth vector field on this Lie group, is going to be left invariant if it is, well, the way that I've defined it, it's LA related to itself for all A, which means it's a push forward. So whenever you do a left translation and you push forward this vector field, it goes back to itself. Okay, so it's invariant under left translations. Okay, so let me write this down again. So this means that if you look at left translation by A, and you take, so this is a left translation, then the push forward of any tangent vector, let's say this is a tangent vector at the point G, okay, this is going to be Y, this is going to give you the same vector field. So this is the push forward will take it to the point LA of G. So it's going to give you the vector of the vector field there. Okay, so this happens for all G. Okay, so you can think of left invariance as sort of saying this. For all A and all G, you have this. Okay, so well, okay, so this part, I mean, this derivative, it's actually at G, right? So the derivative of LA at G. You can think of it that way also. So I've just written star here, but it's the derivative at the point G. And you look at where this tangent vector defined by the vector field goes. Well, it goes to the same vector field. So the tangent vector goes to some tangent vector at the tangent space LA of G, but it's which tangent vector does it go to? Well, it goes to the one that is defined by the vector field. Okay, it's because the vector field is invariant under left translations. Okay, so this is what a left invariant vector field is, so the point is that these things. Well, first of all, so one thing to notice is that what does the left invariant vector field mean? Well, it means that suppose I look at, so let me draw a picture first. So if you have this group, Lie group G, you have this left translations, right? So if I start with the identity element of the Lie group, right? Then I can send that identity element to any element, right? Just by multiplying by some A, right? So if I if I pick an A, this left translation by A will send the identity element there. So then where will it send? So suppose YE is the vector field vector at the identity, then this has to go to so this has to go to the vector field vector at A. Okay, so in particular, so let me write this. So the derivative of the left translation by A at the identity element will take YE to YA. Okay, so this is something that's sort of automatic from the definition of a left invariant vector field. So this tells you that, so once you know what vector is at the identity, what YE is, then you know it everywhere in the Lie group, because, you know, sort of, so now if I, let's say I have another point B, so what should be the vector field vector at B? Well, you look at the left translation by B and then look at where YE is sent, and that's going to be your YB. So you can define, once you choose a vector at the tangent space of the identity, you can push forward to any other point in the Lie group by some left translation, and this would define a left invariant vector field. Okay, so let me just write it as follows. So I can say that a left invariant vector field Y on this Lie group G is actually determined completely by what it is at the tangent space at the identity. Okay, and conversely, once you fix something which is at the tangent space of the identity, fix a vector, you can push forward with all the left translations and define a vector field in the whole Lie group G, and that's going to be left invariant. So conversely, let me write that down. So conversely, if you start with a vector, if you on the identity, you define at any other point YA, you define it by that boxed relation here. You define YA to be the push forward of YE by the left translation. Okay, so it's like this, right? And this defines, so this defines a left invariant vector field. And why is this left invariant, by the way? So so you can ask that perhaps. So why is it left invariant? Well, what do you have to check? You have to check that this property holds, right? So somehow this one we have checked only for the identity element somehow, right? So if G is equal to E, you know, we've defined this, but we want to say that it actually holds everywhere, right? So this is what left invariance actually demands, but it's enough to prove it for the identity element. And now that's just because if you have so what you want to show, you want to show that let's see. So you want to say that
Most like LAB is LA times LB.
Yeah, that's right. Exactly. So if you have, let's say, translation by G1, G2 of YE, so that you can write it as G1 G2 composed with G1, right? So left translations, if you compose, this is because left translations form a group action, right? Here you're using the fact that, you know, things are a group. So this applied on YE, and now this is derivative of a composition is the composition of these derivatives. So you can write it like this, and now this by definition is Y of G2. And so what does this ensure? Well, yeah, so this by definition is Y at G1, G2, right? So you kind of, yeah, so this ensures that, so let me just write this. So G1 at Y, G2. So this tells you that the property holds for G equal to G2, right? So this is for all G1, G2 in G. So from the fact that we knew this sort of thing for the identity element, by definition, you can actually prove it for any other element G2. Okay, so anyway, so this left invariant vector field is defined this way. Yeah, it's also smooth, okay, and then that's also kind of easy because all of these multiplication maps are smooth, okay, so maybe, let me just write down a few things. So Y is YA smooth. Well, it's if you write it in local coordinates, so in local coordinates, you can you have so if this vector that you chose on the tangent space of the identity is something that like this, perhaps, so the AIs are real numbers, then the vector field that you define at the point A can be written in local coordinates. Yeah, so as well, here I'm choosing local coordinates both in the domain and the target. Okay, so around around the identity, I'm choosing some local coordinates x1 to xn. Around A, I'm choosing local coordinates y1 to yn. And so then you can actually sort of write down what this thing is. It's going to be a double sum AI, but the point is that what you get here is these coordinate functions. So these smooth functions and partial derivatives of those, okay, and del yj, okay, and so the point is that these guys are smooth because the left multiplications are smooth functions, smooth maps, right? So this is a left multiplication composed with these are the local coordinates of a left multiplication, right? So yj is the maybe I should draw a picture somewhere. So here's identity, here's my left multiplication, and here's A, and so I'm using local coordinates x1 to xn here, and in some neighborhood y1 to yn. And so in these local coordinates, these LA looks like, you know, y1 composed with LA, y2 composed with LA. So these are, so y1 to yn are what these, yeah, anyway, so you can, so these are the coordinates, and so there's some coordinate functions, and then these partial derivatives appear in the, when you look at the derivative of that, of the map at the level of coordinate functions, and then you're sending this vector that I have here, you're just multiplying by that derivative matrix, and this is what you get, right? So this is and the point is that these coordinate functions are smooth, so you get a smooth vector field. All right, so anyway, this is something maybe a little bit pedantic. It's sort of obvious that if your maps are smooth and you push forward with this derivative, if these left translations are smooth maps, and then you define the vector field by pushing forward as we did, you're going to get a smooth vector field. Okay, but the point is that you get this important corollary, which is that the set of left invariant vector fields, the set, I'll call it something. Let me call it script G for now. It's a set of left invariant smooth vector fields on this Lie group G. Okay, so G is always a Lie group for us from what we know. This is the same as a vector space actually to the tangent space at the identity. Okay, so so this is sort of let me just say isomorphic as vector spaces. And what is this map, or what is this isomorphism? Well, is what I just described, right? So YE, sort of YE mapping to Y. I mean, so we are extending a vector, tangent vector at the tangent space at identity to the whole Lie group to get a defined left invariant smooth vector field. All right, and conversely, once you have a left invariant smooth vector field, you can look at what vector you have at the identity map, and you get a vector there. And so this from what we discussed, this is going to be an isomorphism. And so this is a vector space. So this G is a vector space of dimension equal to the dimension of the Lie group as a manifold, right? So the Lie group has some n manifold for some n, and so then your tangent space of the identity is Rn, right? And so so the set of left invariant vector fields forms a vector space of that dimension. All right, so so this space of left invariant smooth vector fields on the Lie group is actually going to be very important for us because it turns out it's more than just a vector space. Okay, so I've already said I'll go a little bit over time, so I'm going to do a little bit more. I'm going to say what, let me just sort of end with one more definition. So so this definition is of a Lie bracket. So the Lie bracket of two vector fields. These can be defined for any vector fields on a manifold, not just left invariant vector fields on a Lie group. So and we'll see what it means later on. So but right now, let me just introduce it. A Lie bracket of two vector fields, smooth vector fields, of course. Let's call it X and Y in the these are smooth vector fields on M, is a new vector field defined as follows. So this new vector field is denoted by X comma Y square brackets, and so I need to tell you what tangent vector it is at a point P. Okay, and for that I need to tell you what it does to a smooth function. Remember that a tangent vector is a derivation. So I'm going to define a derivation as saying that this the Lie bracket gives you a vector at the point P, which is the derivation xp acting on the smooth function yf. Remember, y is defined on the whole as a smooth vector field defined on M. That defines an operator that acts on a smooth function, give you another smooth function, which you can feed it to this derivation, minus yp xf, okay, for all f in C infinity of M, and for each point P in M. And then the fact is that sort of this, so x, y, p is the derivation at P if defined this way. So it's a tangent vector, And so this defines a vector field, and it's again, it's since x and y are smooth vector fields, it's easy to show that this is also going to be a smooth vector field. All right, and the point is that it turns out that so maybe I'll do it next time, but it turns out that left invariant vector fields on a Lie group G are preserved under this Lie bracket. Okay, so preserved under sort of Lie brackets. So if you take Lie brackets of two left invariant vector fields, you get another left invariant vector field. And so there's this extra operation that you can do on left invariant vector fields, and that's going to be sort of define a Lie, what is called a Lie algebra structure. Okay, so so maybe I'll do it next time. So next time we'll see this. We'll see this, and we'll see how sort of this set of left invariant vector fields is the Lie algebra. So it's a vector space together with this kind of this Lie bracket, and this Lie bracket has certain properties, and so this is called the Lie algebra of the Lie group G. Okay, and anyway, so this is going to be one of the central themes of this course. I want to get to understanding what is called the correspondence between Lie algebras and Lie groups. But for now, we haven't yet gotten to the Lie bracket. I just defined it. The next time, maybe we'll start with next time with the definition, and we'll talk about why this defines a smooth vector field. Maybe I'll do some examples, and then we'll go on to sort of say certain properties of what this bracket is, what properties it has. Later on, why this bracket is defined in this funny way would slowly become more and more clear. I mean, this bracket arises in very naturally in many ways. So that will come later perhaps, but next time we'll see certain properties and say why. I mean, maybe see some examples, right? We've seen some examples of Lie groups like GLNR, and apart from Rn, we've seen GLN and ON, etc. So we'll see some examples in this in action. All right, so any questions? Maybe I'll stop here for now. We went a bit over time, but kind of warned you about it.